think what I'm going to do today, let me check this one. I think I hear an audio. I hear an audio. So in Thermo, see if I can go back to where this might start. Okay. So in Thermo, or maybe somewhere before, you learned that m dot was equal to rho AV. So what you were doing when you were doing things in Thermo is you might have some pipes coming together, splitting apart, and so you'd have an m dot 1, m dot 2, m dot 3, and m dot 4. So essentially what you're doing is sum of all the m dots equals 0. So someone had to decide what was positive, in or out. So essentially you were saying m dot in is equal to the same as m dot out. Now, what you're going to see here is a strange derivation of this same thing, and the only reason I go through this is because it can be extended. Here's what I mean. So if you had m dot times some sort of acceleration term, which really going to put a big bunch of questions marks, like it would be some of the forces, or m dot times rho r across the acceleration. Maybe that would be some of the moments, or in this particular case, sometimes they call it torque. So the question is, how do you get from here to there? And this is where you take this thing called a Rimels transport equation to get you there. So I'm going to kind of just skim over how it's derived and give you the basic points, and we'll just kind of go to the equation. So what we start with is the blue control volume, this dotted blue line right here, and there's a dotted black line that occurs after a second or so, or a millisecond, or something like that. So you have a fixed, just fixed in space and time. The system boundary starts at a certain point, and then it's like taking a snapshot. A certain amount of mass moved out, a certain amount of something moved out, and a certain amount of something moved in. He has this in 3 designations. The CV is the fixed control volume. The controlled surface is the surface around that volume. So he's defining this to be the controlled volume, and he's saying something could be exiting there. He goes through a series of derivations, and what you have to really think about is the system equation is going to be an equation that deals with, for example, when you had a certain amount of energy in there, the system, you might have had a piston in here, and so here's your system. Put a candle under it, you heat it up, and it pushes the piston up. With the system, the amount of stuff in the system didn't change. So here's your piston. So it moved it up. The control volume is such that things can pass the surface of it. In other words, the system is kind of defined as a fixed system. It can pass the control through the control volume. So he goes through all this, and he ends up to the point where he finds that the rate of change across the control volume looks like this, and I'm not going to go through too much of it. And he ends up with, let's see, he's already subdividing it down. So for example, you might have flow through here, you might have the outflow, and this is the inflow. So you're thinking M dot in, M dot out. Okay, so here he has a control volume with more than one inlet and outlet. He defines this term. Now this is something we'll have to pay attention to. Is if you have a surface, now this is a normal to that surface, meaning that if you drew the lines across here, let me zoom in on it. Let's say the surface was defined by this mesh here. And this mesh was sitting here like this. So these are lines of a mesh. Now, I'm going to make use of. So here's your normal vector. Turns out that it is perpendicular to the surface at this point that it originates out of. So this is normal to the surface. So for example, you had inlet, say some flow coming in, getting squishing down. Then the control volume is defined by everything that's in there. The control surface is the red. The normal would point out. It would be perpendicular to the surface. In other words, 90 degrees to a tangent there. And of course the normal points out backwards here, it points forwards here. It goes through this process. Now this is going to be key towards working some of these problems. You get down to the point where, okay, here is your Rimels transport equation. So let's look at each individual term. And for that matter, well, I'll go ahead and do it right here. So here's your normal, and here's your velocity. This term is a quantity per unit mass. And this is whatever quantity that happens to be. And I'll show you how this is, he'll show you how this breaks down to the conservation of mass here in a minute. But let's focus on this. So let's say the flow is going down this pipe, and this is the control surface, all of this. If I drew it in here, and I had a velocity here coming out, then N dotted with V, which is what he has right here, is equal to the magnitude of N times the magnitude of V. This is going to always be 1 times the cosine of the angle between them. In this case, the angle between them is 0. And as a result, that's going to be 1. Now, let's go way back here into the fact that the flow comes in at a larger thing, shrinks down like that. Your normal points this way, and your velocity points this way. So this time, what I'll do is put a designation in the normal at the location where the velocity is going in. So, here, the inlet times normal at the inlet is equal to V at the inlet times the magnitude of the normal at the inlet, which again is 1, times cosine, these are 90 degrees, I'm sorry, 180 degrees from each other. You remember the cosine? It's like this, starts here. There's your 180. So this becomes minus 1. So that would be that. So suddenly you start seeing something. The sign of in or out is associated with this term. This designates the surface of out equals to a positive number, whatever number comes out of this. And in associated with a negative number. Why? Because when it goes out, the angle between them is 0. When it comes in, angle between them, 180. What if you're looking at the wall? Here's the cool part. Okay, let's look at the wall. Okay, if you're looking at the wall, I'll even go in and change it to the flat. So here's your normal, and here's your velocity. So I don't know what to designate this, except so I'll just say 3. So V3, oops, dotted with N3. This should have the designation here, and I should say out here. That's equal to velocity magnitude at 3, normal magnitude at 3, always 1. Cosine, now they're 90 degrees to each other. Cool thing is, there's your 90-degree point. That is equal to 0. So this is equal to 0. What does this designate? Whatever this is, mass is not flowing out of the wall through this. Wherever you're looking at here, wherever you're at, no matter how weird this shape is, let's make it weird. Here's one normal. Velocity has to go this way or the other way. Here's your normal here. Velocity at this point has to go perpendicular to it. If it's not going perpendicular, what's happening? Here's your normal. If it's not going perpendicular, it's going at some angle, meaning there is flow. Here's your velocity. You have a component going through the wall. You have a component going along the side of the wall. But you have a component of fluid coming out of the wall. That doesn't happen. So there's never a discussion about that in this concept. When you're talking about m dot in is equal to m dot out, there's never a discussion of the m dot through the wall is 0. It's kind of stupid to have that discussion. M dot through the wall, through a solid wall, is equal to 0. So no one ever discusses that. But in a mathematical sense, this is what's happening. Here's that dot product. And the fact that they're 90 degrees from each other means doesn't happen. So the question is, what is the B? The B is defined as some sort of substance per unit mass. So in other words, B of the system would be what? Well, let's say that, mass. And this means B, the little b, is the mass per unit mass. So in other words, B is the big B per system per unit mass. And he says that down here in a little bit. So what he does, he goes through a physical interpretation of parameter B, and he starts talking about it. So the other thing that he brings up is this. Okay, let me change to this. He talks about this, and he talks about no transport across the surface. So here he's drawing surface of a faucet. Okay, so here along the edge of the faucet, you're not having mass squirt out at you here. You're having it squirt out this way. So you're having mass come into the faucet down here, basically like that. Why is it less than 0? Well, because normal points one way, velocity points the other way. They're 180 degrees apart, meaning that here velocity's pointing this way, normal's pointing that way. Here along the metal surface of the faucet, nothing's happening because this vector v is 90 degrees to that vector n, meaning nothing is shooting out of the wall. Now, if you drill a hole through this, you'll have a little outlet in the end. Then it's considered an outlet, and then it behaves just like that. Now, you read this about the relationship between the material derivative. You get down here. Okay, the other thing he says is about steady effects. Okay, it's a steady flow, and that means this term, whatever that term was zero. Now, if you go back up and look at it, for the original equation, let's look at what this term is. I'll try to erase that. Okay. Let's take for a moment now. He will take it later. Let's assume for a minute that we're going to put in the mass. If we do, this number becomes 1, and this becomes 1. Now, and we'll talk about this in a second, but let's look at this term. If it's steady state, what does this term mean? If the density, if the mass inside the volume, remember this is mass per unit volume, I'm putting it in there and integrating over the whole volume, which means that this is nothing more than mass inside control volume. If that does not change, this term completely is gone, meaning, you get back wherever that was, meaning you get back that. Get back that term by itself without the time derivative. Now, there are unsteady effects, meaning this. You have to consider that. Sometimes that's very hard to actually do in the real world, much less a problem. So what he's doing here, look at this. He's designating a normal. He has a velocity going in. He has his control volume surface, this little blue dotted here. He has a normal going out, and this going out. He has normal designated right here. He has the velocity right here. And if you dot each one of these, you'll find the going out is a positive, like v dot n going out is just the positive velocity. V dot n here is equal to nothing, no mass of anything that's coming out through here. And since these are going in opposite directions, v dot n here is equal to the minus 2. So remember that when you're going through this. We'll do a problem in a minute. So we're going down here. So he talks about moving control volumes. I'll come back and talk about that later. Because the terminology doesn't match terminology used in most books. With the selection of control volume, usually that's pretty apparent. And he gets all done and he has Rimels transport. Then what happens to you is you go to the next chapter. And in the next chapter, first thing he does, hang on. He says, finite control volume analysis. You read all those, but here's the first thing he does. He says, conservation of mass, continuity equation. Now, if you take a real close look at this, he says, okay, a system is defined as a collection of changes. Conservation of mass, simply stated, time rate of change of a mass is equal to nothing. So on the left-hand side of this equation, that's what you got. But if that is the case, this means this. You have designated your B to be that. Then guess what you do? Now somewhere he's supposed to say this in here. Oh, here we go. If B is the mass. The little b is 1, or little b equal to the big B, keep losing that S, over the mass of the system. Now, I was using a smaller case earlier, so I guess he's using a bigger case, so we better do that. Guess what you get? You get this. Now, you look at the left side, and if you're integrating over an entire system, and the system is defined such that that's the case, then the left-hand side is going to be naturally 0. Usually, I see this left-hand side written right in most books as being this, the mass of the system over dt, and then they'll just say that's equal to 0. So I usually don't see them writing this way. That's okay, because the next thing you see, well, I'm trying to see the one where he has the complete, oh, here we go. You see this. So this is your continuity. Now, you may be thinking, what? This doesn't make sense. Until we do, let me use the keyboard here. Oops, wrong button. Uh-oh, what did I do? What did I put the thing? Uh-oh. I don't know what I did. Hope I didn't mess up anything. Let's take this, get over here, monkey around with some examples, and you'll find something weird out of here. Okay, so here's what we'll do. We'll start with a case in which we make the flow like so. Let's say flow's coming in here at 10 meters per second. To make things easy for myself, I'm going to say the area is equal to 5. And I'm going to say here the area of 2 is equal to 1. Now, you already know that, you know, rho AB1 is equal to rho AB2. And if you want to cancel the rho because they're constant, then you have, on the left-hand side, you have 5 times 10 equal to the area at the exit 1, so velocity 3 is got to equal 50. And then you're like, okay, this is my continuity. This is what I'm used to. Now, I'm going to say we're going to do things a little bit different here. Here's what we're going to do. We're going to designate a normal. We're going to designate a normal 2. Now, you can designate normal around here too. I'll say normal wall. Here's your velocity along the wall. Okay, if you go dock these, that's fine. Let's do this. First I'm going to do say it's steady state. This means this term, not this term, but the whole term, the time rate of change of this term, this whole thing is going to become 0. So this means that integrate around the control surface of rho velocity dot n dA, and it has to be equal to 0. What this means mathematically is I start somewhere and I integrate around the whole thing till I integrate across and come back to myself, and then I've completed that integration. So from an engineering sense, what we'll do is we'll subdivide into 3 regions. The one, the wall, which is all this, and the 2. So I'm going to do that. Control surface of rho 1, velocity 1 dot n1 dA. I'm going to do this way because I've got to do around the whole control surface. This actually, in the book, it should say this. It should have this, that you're supposed to integrate around the whole surface. So there should be a circle designated. You're supposed to integrate around the whole circle. So if I do this, and I just integrate over surface, say 1, plus I'm integrating row wall, velocity wall, that end of the wall, the area of all the walls. So there's a lot of wall area here, all around in here. And then I basically integrate in the exit, velocity to exit, which I'm calling 2. And the area of the exit, which I'm calling 2. Let's now look at each of these terms. These terms. These terms. And then these terms. First thing I can recognize about 1 is that this. Here's the thing. They're going in exactly opposite direction, meaning they're going 180 degrees apart. Which means V1 dot N1 equals to the magnitude of V1, magnitude of N1, which is 1, times cosine of 180, means this first term minus rho 1, magnitude of V1 times the area 1. Why is it minus? Because that is minus 1. That 1. So I get the minus sign here. What do I get here? So here, let me slide this over. Uh-oh. Again. I don't know if I got it all in either. Yeah, I'll slide it over and shrink it. And shrink it further down. And then I'll put a little shade over. Okay, there you go. Right, like that. Put the escape and then put a little shade over it. How do I get to this one? Okay. The wall, that end wall, is equal to magnitude of the V wall times in at the wall, which that's going to be 1. But then cosine of 90, which that is 0. So I basically can say rho at the wall times 0, the area at the wall. That 0 is going to take this whole term and trash it. And then finally, the exit, the two are going exactly in the same direction. So V2, the magnitude, times N2, and that is V2 dot N2 equals to times cosine of nothing, which gives you this time rho 2, V2, magnitude. You can put a plus sign there, that's what you're getting, and the area 2. Now if you look at this, and let's assume we have a constant velocity across this whole area, then what you're going to get is minus V1, the magnitude, A1, plus, that term goes away, so you get this term, rho 2, or exit, whatever you want to call it. Now I'm dropping the subscript on the density because it's considered to be constant density here. And it's equal to 0. When you look back at the equation, the right-hand side was 0. So lo and behold, you have m dot in equals m dot out. Now you may ask the question, why in the world would I consider doing this in the first place? Because I know that to begin with. And so, why is this an exercise in futility, or is this just some sort of person who decides they want to make things more complicated than they are? What's the purpose? Well, let me show you what the purpose is. Okay, let me get past here, and I'm going to go down to momentum. The reason you want to approach things this way, okay, so you're still doing m dot. M dot, M dot, M dot. That's fine. That's great. There's nothing wrong with it. Now, no, not interested in that yet. Now let's look at derivation of linear momentum. So he talks about Newton's second law, puts it in here. Then he comes out and says, okay, sum of the forces in the system is going to be equal to the change of the system of the velocity times the density integrated over the entire volume. And then it comes down to, now usually this is written in other textbooks as this, dmv dt, and that's okay. And then what have you done here? You got to look at what you've done. Okay, so I think maybe I have to go to the next page, but to find the, okay, so anyway, maybe he did it up there, but in any case, if you look back at Reynolds transport down, it said this, dt, some quantity v of the system is equal to v, special t, an integral of the rho times the little b, d volume, plus the integral over the control surface of rho, little b, the v dot n dA. So if you look at this, this means, and somewhere in this text it should say it, v of the system is equal to mv. This means the little b is the big B divided by the mass, which means this. So by simply inserting a b of a velocity right here and right here, what you have is this term on the left-hand side. Newton's second law tells you that this is the sum of the forces. So you get down here, you should see the boxed equation that says this. Sum of the forces on a control volume is equal to, now this is the little b term, which now turns into the velocity. Now, that's the linear momentum. Let's go back to our problem. By the way, we knew, let's go ahead and designate this, that V2 was going to be 50, right? So now I want to know how much force is this person having to hold this nozzle back, the fireman standing there holding the nozzle. Yeah, take a look here. First thing I can do is I can say sum of the forces, and it's often kind of beneficial to do this in two diagrams. In other words, I'm having to hold this, I'm having to put a force here on this. I'll say Fx. I'm not going to worry about anything past that. I'm going to say the exit has pressure is equal to 0. Let's say right back here, way back here, the pressure is equal to, I'll just say P1. So, now, go over here, I'll redraw this thing, but this time, area is equal to 1, velocity is equal to 50, area is equal to 5, velocity is equal to 10. Now, sum of the forces in the x direction is equal to, we'll say it's steady state, but I'll go ahead and do this over the whole control volume of V times rho d volume, but we're going to say it's steady state, so this term is gone. And I'm going to do the other term. The term is integral over the whole control surface, which should have a circle there, the velocity. Now I'm going to go back and do this. I'm going to do a generic form of it first. V with a rho, V dot N dA. Now guess what? You already know this. This came from continuity. And so now I'm going to look at take this and do a free body diagram. Let's say I have a force right here to the left, to the right, which was P1A1, P1A1, and I'm going to have to hold this nozzle, plus Fx, which I don't know what it is equal to. So that's the free body diagram. Now this is steady state, so this term's gone. So now on the right hand side, okay, so take a look here. I have a vector here, I have a vector here, and I have a vector here. This is a scalar, which is nothing more than m dot. So this dot product gives a scalar. Again, the vector comes from up here. So, in fact, I want to take this and write it down. dx, yx, because I am summing the forces in the x direction equal to. This way. So the reason it's f of x, or vx, is because this is f of x. In rho, v dot n, dA. Now, I'm going to take a few seconds, and I'm going to look at this. I had 1, so let's designate them again. 1, 1, 2, 2. So I still have the P1. Okay, what is going on here? Well, P1, A1 plus Fx, whichever the fireman's having to hold the hose. And I'm basically going to say Vx at location 1 times rho V1. But guess what? I'm talking about V1. Come on. Normal goes back this way. Over here, normal goes that way. This is normal 1, normal 2. It was inlet, this is negative, this positive. So, I should have a negative V1, I'll put a parentheses or something on there, times A1 plus V2x rho plus the magnitude of V2 A2, and suddenly, if you think about this, I had this term earlier. That was the m dot, and guess what? Both of these are equal. So let's assume this is water. Now, the x component for the velocity at 1 is 10. So what you get is 10. Let's assume it's water. What was the unit? I was using meters per second. So this means the distance 5 plus exit velocity was 50, I think. Density of 1,000. Vx happens to be the exit big. So, and that's what we had before. Okay, I wish this thing needs to get popping up. So it's 50 here. The area is just 1. So let's say you had a pressure of 1 here. And then you had an area of 5 times. That only gives you 5. Is equal, wait, plus Fx equals to. You see, that's 100, and it's 100,000, so it's 500,000, if that's right. And plus, okay, 5 and 5 is 25, and then I got 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. So it looks like to me, Fx equals to 2 million newtons there, whatever, you know. Yeah, because I guess if that's the case, 50 coming out pretty fast. So you're, and yeah, I need to bring this over and take 5 off of it, but this tells you the force that's actually happening. And what I'll do next time is I'll go through some problems that should lay the groundwork of how to calculate the forces. Let me buzz down here to the problem. And we'll start with the simple one. Not right now, but in the next time. Okay, come get down here. Okay. Good grief. Long chapter. Okay. Now these start with continuity. And so what we'll do is we'll start with continuity next time in these problem sets. And then we will go to, he does split these. So this is applications of linear and nonlinear. So I'll do this one. I'll do that one. I'm not sure I can do them all at the same time there. I'll do this one. I'll do this one. What's this false? No, it doesn't. On the same page. This one's interesting. So I'll do this one. And definitely want to do this one. And so I'm going to go ahead and shut it down and we'll pick it up next time. Okay, chapter 6. Okay, so I'm going to go ahead and cut it down.